Many people have seen two very different formulas for calculating the standard deviation of a set of observations and wondered which one is correct. In this video, we will perform the calculations to show that the two formulas are actually equivalent. Let's first recall the formulas for finding the mean x bar and the standard deviation s for a set of n observations that comprise a sample drawn from a large population. To compute the mean, we sum the observations and divide by the number of them. This value is used to describe a typical observation. The standard deviation measures how far, on average, the observations fall from this typical value. Remember that when we use a sample standard deviation to approximate a population standard deviation, the approximation is better when dividing by n-1 instead of n. There is another alternate formula for calculating standard deviation. It's sometimes called a shortcut formula because it doesn't require computing the mean first. This formula has several advantages for calculating standard deviation. As already mentioned, it doesn't require using the mean. This is helpful for at least two reasons. It obviously cuts down on the number of calculations required. Also, if the mean was approximated, that error would be compounded when using the mean in additional calculations. Although the two standard deviations formulas look quite different, they are in fact equivalent. We will perform the algebraic calculations to exhibit this equivalence. Note that to show the standard deviation formulas are equivalent, it is enough to show that the two numerators are equal. In our calculations, we will use two facts. One is the definition of x bar, and the other is the equation we get when multiplying that definition on both sides by n. Let's explicitly perform the algebraic calculations. We will start with the sum of the quantity xi minus x bar squared and expand the square by foiling to get xi squared minus 2xi x bar plus x bar squared. Then we distribute the sum over each term. Even though we haven't explicitly written the index variable with the summation symbol, note that we are summing over I values. So 2x bar is constant in every term of the middle summation. Therefore, we can factor it out using the distributive law. Now we will use that summing the xi values gives n x bar, and adding n copies of x bar squared gives n times x bar squared. In the middle term, we rewrite x bar times x bar as x bar squared, and notice that x bar squared appears in two terms. We factor out the x bar squared and combine the coefficients minus 2n plus n for a minus n. Next, we replace x bar with its definition, sum of the xi's divided by n. To square a fraction, we can square the numerator and square the denominator. Finally, we cancel one factor of n in the second term to get our desired expression. This establishes that the two standard deviation formulas are in fact identical.